Hello, everyone. Thanks for coming here. So today our speaker is Yash Pote. He's a final year PhD student at the National University of Singapore. He's working with Kuldeep Meal, and he's interested in distribution testing and formal methods with a focus on developing practical tools. Sorry, for developing like distribution testing tools for practical settings. So without further delay, start.
Thank you, Argyris. Can I just have all of your names? I'm just curious.
I'm Therese, faculty member. Eric. Sharon. Sarah.
Matt.
Lehan.
Jeremy.
Okay.
Okay, so nice to meet everyone. I'm Yash, and I'll talk about the work I've done as part of my thesis. So the title is Towards Practical Distribution Testing, and this is jointly with Gunjan, who's a postdoc at NUS, Saurav, who is faculty at ISI, which is in India, and Kuldeep, who is my advisor, and he's at U of T. So let me get right into it. So these are the main characters of today's talk. I'm going to be talking about high dimensional distributions. So high dimensional distributions are commonly used to model data, which has like complex relationships, such as text data, images, signals, or even things like molecular structures. And high dimensional sampling is a key part of many areas of computer science, such as, for example, in software development, you have fuzz testing, where you are supposed to draw samples from the input space of a program, and which can be very structured and difficult to sample from. High dimensional sampling is also important in scientific simulations and also nowadays in generative modeling. But typically we see that sampling from high dimensional models is in general intractable for many real world problems. For example, exponential random graph models. So if you want to sample social networks or just networks, you typically want to use this model, and it's computationally hard to sample from these models. Also from certain graphical models and icing models. So what a developer usually does is that they build heuristic algorithms. For example, for many problems, people use MCMC algorithms, and you can think of them as heuristic algorithms because they are not really used with theoretical guarantees. For example, there are some magic parameters such as burn and time, which are typically used in practice with MCMC algorithms. And when you're dealing with things like language models, there are also some heuristics which are chosen by the developers or users, such as top P or beam search. So a question every developer has is my algorithm correct? Like if I intend to sample from a distribution P, and if I am sampling from Q, are P and Q close? So I've focused on this question, and this has been my research goal, to determine whether distributions P and Q are close. There are two variants of this question. One is the decision variant, where you want to know if P is exactly equal to Q, or if P is significantly far from Q. And there's a harder version, which I'll call the estimation version, where you actually measure the distance between P and Q up to some tolerance epsilon, which is also given to you as input. So in this talk, I'll focus only on the second problem, the estimation problem. Like given two distributions, how do you measure the distance? So more formally, this is the problem statement. You're given two high dimensional distributions P and Q and a tolerance parameter epsilon. And high dimensional in this talk, I'll consider it to be the Boolean hypercube in n dimensions, where you can think of n to be something large. So which means that we want algorithms which will be polynomial in it. And what does this model? This models things like text, which can be represented as binary strings or even images, or basically any data which is stored in a computer. And the output has to be alpha, which is an estimate of the distance, and it's within additive epsilon of the distance dtv p of p and q. And you're also you're also allowed to make an error with probability 1/3, which means that you have to be correct with probability at least 2/3. So let me talk a bit more about the notion of distance I've chosen. So there are many notions of distance between probability distributions, but I'm going to talk about the total variation distance in this talk. So this is how it's defined. It's defined as the max of P sigma minus Q sigma over all elements of the domain. Max of P sigma minus Q sigma and 0 over the entire domain. And graphically, you can see it's the blue area in this graph between the distribution P and distribution Q. And yeah, that's the total variation distance. It's very fundamental in many different areas of CS. For example, Markov chain mixing time is defined with respect to total variation distance. It's important in cryptography, approximation algorithms, and also in some learning algorithms. It also has an operational meaning, which kind of motivates my work. The operational meaning is that, let's say you start with a program with samples from a distribution P. And let's say maybe P is either very difficult to sample from, or it's very expensive to sample from. So you would rather you replace it with some Q, which is somewhat easier to sample from. And you hope that your algorithm gets faster because of this, but you also hope that your algorithm doesn't get much worse. So you can interpret the TV distance as putting a bound on how much error is added. So you can say that if P is replaced with Q, then the distance of P and Q under the total variation meter sort of gives you a bound on the error of your algorithm. So now that I've talked about the notion of distance, now let's take a deeper look at the distributions. Like, what do I mean by distributions and how do you access them? That's really important in real life. The most standard model is the black box model, where you say that you don't know anything about a distribution, you're just getting samples from it. It's like a black box. And you get a series of samples, and then you use these samples to do some statistical tests, let's say. So that's the most generally studied model, and it has been studied for a really long time. However, because it's a black box, the sample complexity of many tasks is exponential in n. For example, for distance estimation, you're going to need 2 to the power n by n samples. So that's not really practical if you want a very large n. There's also a white box model where you can have more powerful access to the distribution. You can look inside the program or look inside the process which is generating the distribution. And you can query things like what is the point, the most likely element. You can make these queries. So estimation in very few samples. But then again, it's not very widely applicable. Like you cannot do this with many probabilistic models or even most probabilistic models. In general, it's computationally intractable. For example, if you just want to find a point probability in a graphical model, then it's going to be sharp p-hard, or even an even simpler model like a DNF or a CNF. So we have these two models, a black box and a white box model. And we want something which is practically useful. So we are going to look between these two models. We are going to consider a gray box model where you have limited access to the distribution, but you have more access than a black box model. And the queries are tractable yet expressive. So for this, we use conditional sampling. Like we consider, we assume the ability to draw conditional samples from the distribution in a specific sense. And we show that then the problem becomes computationally and statistically efficient. So it's not like we want to tackle more models than the models for which we have white box access, but also we want to do it fast. Like we want to have polynomial time algorithms. So in this talk, I'll look at white box models for distance estimation and gray box models. So I won't be talking about black box models. That's a very well studied topic. Let me start by talking about the background. So our agenda is to develop practical algorithms that take two distributions and give you the distance. And there have been a lot of works on this topic quite recently, also in the last 10 years. But there hasn't been a work about distance estimation. And all we know is that there's a lower bound of n by log n. So n is the number of dimensions, if you remember. And we know that there's a lower bound of n by log n for distance estimation, but there was no upper bound known. And of course, there's the naive black box upper bound of 2 to the power n by n, which was known. So yeah, we'll try to find a polynomial time algorithm for this problem. And in case of the white box access models, there had not been too many studies mapping out which models exactly you can do this white box access on and find out the distance. So we are also going to construct a map and we are going to consider a set of ML models and see that, okay, can we do this query? Can we find out the total variation distance between two models? So that's the white box part of it. And the gray box part is we are going to design a polynomial query algorithm for this distance estimation. So we're able to find such an algorithm and we'll also build the map later in this talk. And interestingly, we were also able to implement algorithms for both of these models. And like find good enough constants and find optimization so that they work for reasonably sized models.
Can I ask a question?
Yeah.
What exactly is the lower bound for here?
So the lower bound is the omega n by log n.
Yeah.
So that means it's in the gray box model, like given the kind of conditional access we are going to use. And if you are given two distributions, then we know that you cannot do better than n by log n. And yeah, so yeah, we already know that it's going to be at best a polynomial algorithm. So I've set up the problem by now. So if you have any questions about the problem setup, you can go back. Not, I'll continue.
Can I ask, this could be an embarrassing question, but which is the reference, CDKS 20?
I think it's Cano, K is Kane and Stewart. And I think I'm not sure about D. Yes, I think so. I might be wrong about this. Yeah, if I had to guess.
Okay, I thought they had an upper bounds paper, but maybe I'm just getting them confused. Anyway, it's not a big deal. Thanks.
All right, so this is the main ingredient for the gray box testing. So it's conditioning. So the standard notion of conditioning where you have a distribution Q and you're allowed to give a query set, which is just a subset of the domain. And then we assume that the distribution is going to return samples from the conditional distribution. So yeah, it can be defined as this. So let's say T is the subset and the condition distribution QT sigma is just the probability of sigma divided by the total probability of all the elements in the set T. And so conditioning in general is quite difficult to implement. Like you cannot work with arbitrary sets, right? Because there are 2 to the power, 2 to the power n sets. How will you even represent such a set? So we work with the restricted notion of conditioning. So we'll work with subcube conditioning. In this, you are allowed to condition on only the subcubes of the domain. So our domain is the Boolean hypercube. So you can condition on some particular subcube. In fact, we'll use an even more restricted notion. We'll say that you're allowed to give a string row, which is of m bits, at where m is less than n, and you're allowed to condition only on the prefix of m bits defined by row. So which means that if you give me a string of 3 bits, I'll fix the first 3 bits, and then I'll sample from the distribution condition on the first 3 bits being row. So this is a more natural query model than like arbitrary conditioning. For example, in databases, this would represent the select query where you fix a particular column or fix some values of some columns. That means that you say that, yeah, I'm in a database, go to this column, fix this value, and then only look at the entries which match that query. And also in language models, you can think of prompts as specifying subcubes, right? So you give some, there's a very large distribution over strings, and you fix the first few words or first few tokens, and then you get a sub distribution on the remaining part of the domain. So you can visualize it this way. I'm going to use this tree representation. So you can think of this being a 4-dimensional distribution on 4-bit strings. And you, let's say, so yeah, so conditioning would look like removing the tree and only looking at a particular subtree, any particular subtree. For example, if you give 0, 1 as the query string, it would mean that you only look at the tree subtree rooted at 0, 1 while ignoring everything else which is in red. So there's a very simple distance estimation algorithm known. It has only 4 steps. So first you draw constantly many samples from one of the 2 distributions, let's say P. Then you find the probability of that sample in Q, the probability of sample in P, and you return the value of this estimator. So note that M is just 1 by epsilon square. So it's constant and does not have N in it, where N is a number of dimensions. And yeah, you find the point probability in both the distributions and just return this estimator. So there are a few problems with this. Once you sample from P, there is an algorithm known which takes n to the power 5 queries to find P sigma. But there's no algorithm known which can find Q sigma. So remember, you have sampled from P and you're trying to find the probability of that element in Q. So I'll go into more details. But these are the 2 big problems. One is the n to the power 5 runtime, which is a lot. And also an even bigger problem that you don't know what Q sigma is.
Sorry, remind me, what was the difference between P and Q?
So you took the samples from P, which means that P is likely to have a non-zero mass in, sigma is likely to have a non-zero mass in P, but it can easily have a very low or even 0 probability in Q. Right? So it's typically easier to find P sigma rather than Q sigma. Like if you had sampled from Q sigma, that would be the other.
How was you given to me?
So you have subcube conditional access to it. So you can draw samples, and then you can also give some small string or whatever, some string, and then it will give you samples condition on that string.
Can you just give it the empty string and that gives you the probability?
If you give it the empty string, it's not giving you the probability, it's giving you samples. So yeah. So in this, what's happening is if you give it the query string 0, 1, then it's sampling from the subtree.
And so why can we get estimates for P but not Q? Don't we have the same access?
Yeah, so what can happen is, let's say you took a sample from P, right? But it has 0 probability in Q, which means you'll never see that element, right? But okay, then it has 0. But what if it has very small probability? Then you could find out, but you'll require like an infinite number of samples.
Sorry, this is something I don't understand because the smaller probability things should not matter, because you're just trying to estimate the KD distance, and if it's less than some epsilon factor, it's okay.
Yeah.
I'm not sure why we're not able to estimate the probability in Q depending on epsilon, just within some added epsilon factor for any sigma I.
We can find it up to an additive factor, yes, but for the estimator, we need a multiplicative factor. So see, we are dividing Q sigma by P sigma. So an additive factor, let's say both of them are very small and Q sigma is extremely small. Then if you have an additive factor, it will mess up.
Yeah. Thank you.
Any more questions?
Which sorry about this, but which reference is CR14?
I think it's Canon and Ruben field. Yeah.
Okay, I thought they were using an eval, not a cond model in that paper.
Yeah, so they convert con into eval using n to the power 5 queries.
I see. Okay, that makes sense, I think. Thanks.
Yeah, so yeah, in the n to the power 5 paper, the authors had used a conditioning oracle, not a subcube conditioning, but a more general conditioning oracle, and n to the power 5 calls. So it was a more powerful oracle, and yet it used n to the power 5 calls to simulate eval. By eval, I mean the ability to find p sigma. So you want to improve that. So here's a more efficient algorithm to estimate p sigma. And we want a multiplicative estimate of p sigma because we are dividing, so we can't work with an additive estimate. So what we're going to do is we're going to use the stopping rule, which is a nearly optimal way of finding the probability of any marginal. And what we do is we start from the top, we start from the empty string to start sampling, and then we see how many of the samples have one as the first bit. Then you condition on one, and then you sample from the resulting subtree, and then you fix the next bit, and you go all the way down, and you take a product of all the marginals. So I have a visualization so that it's easier to see. So let's say we have been given the sample 1001 and you want to find its probability in the distribution P. So we can use a chain rule to decompose the probabilities into 4 marginals. We can say the probability of 1001 is just probability of 1 given the empty string, 10 given 1, and so on. So you draw a lot of samples and you find an estimate of how many samples have the first bit set to 1, which will give you an estimate of the first marginal. And then the second marginal, third marginal, fourth marginal. And then you have an estimate of the probability, an unbiased estimate of the probability. You still have to take care of the error, and you still have to bound the sample complexity or the query complexity. So the first challenge here is that each marginal can be, you have to estimate it up to some constant factor, and each marginal can be arbitrarily small. And there are also n of these. So the query complexity is going to look something like this, apart from other factors. So we show that if you sample from, if sigma is sampled from P, then in expectation, all marginals are going to be large, which means that you're going to get an n square query complexity immediately and quite easily to estimate P sigma. So yeah, that's why we made a distinction between P and Q, because in P this is possible, because in expectation all marginals are small. So 1 by that marginal is not going to be a lot. And then if you take sum over n of these, it's still around n. The other challenge is that now you have sigma, but it can have some arbitrarily small probability in Q, even in expectation. So what are you going to do about that? So for this, we do something different. We actually find another distribution D dash. In fact, we show that for every D, there is a nearby distribution D dash, such that it's close to D and it has all the good properties you need. So for every D, there's another D dash within, let's say, epsilon by 10, where all the marginals are large. Every single marginal is lower bounded by around 1 by n. And the new distribution is also easy to construct and also easy to sample from. So given any D, we basically add some sort of noise to make it make it easy for us to continue with our test. So using this, so now, like, even if you have a sample, you can easily estimate the probability in the other distribution. Because the marginal is lower bounded, now you only have to sample, let's say even if all the marginals are around 1 by n, still need to draw only n square samples to, or let's say, n square samples to find the probability up to a good, like a good margin. And this is enough to complete the test. You just run the test with a smaller epsilon to account for the new error that you have added. You have added an error of 2 epsilon by 10. So you run the test with 8 epsilon by 10 and then you're done. So these are the two issues we solved to bring down the complexity to n cube and like also make it possible. Like there was no algorithm known before this. So now there's a lower bound of n by log n and there's an upper bound of n cube. So we are like working towards making, like, closing that gap.
I'm sorry.
Yeah.
This is a good question, but like you have query access to Q as well, right?
I have identical access to P and Q. I only sub-Q queries.
And you're making distribute the like Q prime using those like in a gray box.
Yeah.
Okay, so you construct.
Yeah, we don't explicitly construct it. So it's like we get a sample, then we do something to the sample so that it simulates access to D dash. So yeah, without explicitly constructing it, we were able to. So yeah, that's the easy part of it, that we don't have to do anything, just add noise.
What about the other maybe naive approach that says maybe actually if the probability mass was small in Q, I could just think of it as zero. So if I get very small marginals, I could just put zero in my estimator. Does that fail, obviously?
Let's see. Was Q in the numerator? Okay, let me think about it. So you're saying if it's less than epsilon by n, which you can confirm using.
So here, this essentially says if my sample had very small mass in Q, I'm going to pretend it has large mass by looking at
Yes.
this other distribution instead.
Yeah.
Kind of simulating access. The other thing I could do is, as I'm
Rounded.
going through my process, if I see a small marginal, I just go, I'm gonna stop trying to estimate it, just think it's zero instead.
I haven't really thought about it.
Okay.
But yeah, interesting. I would like to think about it. Any other?
Like on one hand, you're saying if it was small, then you're doing some data to say that, okay, I'm gonna use large. Here you're saying just gonna ignore it and say zero. And you're saying exactly like literally.
I mean, my first guess is that it feels it should be the same thing. It might end up being a little bit easier, complexity theory-wise, or it might be exactly the same.
So the problem there is all of the marginals could be epsilon by n. And then you could be spending n cube many samples.
So it would still end up being the same complexity. That's fine.
Yeah. But the thing is, I'm wondering if it, like, we still want to improve it. We still hope to get n square. So we thought this would be the way to do it. Okay. So then we decided to try it on some real world sampling benchmarks. So what we did is we considered combinatorial samplers. So these samplers are able to sample from combinatorial spaces, which are usually hard to sample from. For example, you can think of like sampling satisfying assignments of a CNF or sampling K colorings. These problems are typically, it could be NP hard as well. And that's why sampling is non-trivial for small n. So right now we have like somewhat large constants and also n to the power 3. So that's why we wanted a hard enough sampling task with a small n. So for example, the problem we are going to consider the problem of sampling from circuits. and that's already hard for n equal to 70. And there are many heuristic combinatorial samplers available, which are typically used in software verification in software verification. So two of the most used ones are CMS Shen and search tree sampler. And both of these are based on SAT solvers. So SAT solvers are very complicated pieces of software which solve NP complete problems. And these heuristic samplers add some sort of randomization or random branching or some sort of heuristics to make the satisfying assignment returned by these SAT solvers to be more or less uniform. But it doesn't come with any guarantees. So all of these algorithms are like designed intuitively, and then they are sort of tested on the sampling benchmarks for uniformity. So they draw a lot of samples and then they try to draw a histogram and see that is this what we expect? Is this close? But there are no good statistical tests because the domain is very large, like 2 to the power 70 is pretty large. So we use these ISCAS 89 circuits, which are kind of popular sampling benchmarks. And in short, we find that around between 40 to 50, for n between 40 and 50, the conditional estimator starts becoming more efficient than the naive exponential time estimator. And so you can see that the y-axis, it's kind of small, but the y-axis is in log scale. So you are better off using the conditional estimator after, let's say, definitely better after n to the power 50. So we computed the exact constants. The constants turned out to be something like 4.5 into 10 to the power 5, which includes the epsilon. So yeah, when we run the test, it's with all the guarantees. So if you want to preserve all the guarantees, this is the sample complexity you will get. And yeah, the result is already guaranteed by the theorem. So in summary, we designed the first polytime algorithm to determine the distance between distributions up to additive epsilon. And we also implemented it. We are trying to close the gap between the n by log n lower bound and the n cube upper bound. So let me go to the next part of the talk, which is the white box distance estimator. So this is going to be much shorter than the first. In this, we are considering a different problem. In this, we are going to consider models which are for which we have powerful access, and we are going to consider the computational complexity. So now the problems are a bit different. For example, if you want to find the point probability of an element in a distribution or in a probabilistic model, it becomes sharply hard, which is like for even very simple models. For example, if you had a uniform distribution defined by a DNF, and you were asked what's the probability of an element in the distribution, then it's sharply hard. But luckily for us, this distance estimator still works if you have access to approximate probabilities, Q and P. So that makes the problem a bit easier. Because if you finding approximations is computationally easier in many cases. Like depending on the structure of the model, it can be in P, can be in DPP, or it could still be NP hard. And these are 3 different cases. It could be in P if there's an FP task so finding the probability of an element can be reduced to a counting problem. And for many approximate counting problems, there are these algorithms known as FP tasks, which is fully polynomial time approximation schemes. There are also randomized schemes for a larger class of problems, and for nearly all approximate counting problems, they can be solved using an NP variable, which is in PPP to the NP, including sampling from CNFs or the hardest problems. So what we did is we now considered models and we tried to find out how hard it is to solve the counting problem on those in order to determine the computational complexity of determining the distance between models. So we looked at, so yeah, these are all the results we have in just this one slide. So we looked at probabilistic circuits, which are a popular class of ML models. And these are defined using a circuit which has distributions at the leaves and it has some structural restrictions. So these models are used where you want your models to be very predictable, where you want to have the ability to ask questions like what's the probability of an element which we are going to use, or things like what's the max likelihood element in the distribution, and all of these queries, and you want a guarantee that they can be answered quickly. So these are a subclass of distributions or models which we consider in our paper. And there's a hierarchy of them, which is like the most expressive models are at the top, but the most tractable ones are at the bottom. So we looked at each of them and we tried to find out in which case could you really find out the distance between two distributions. So yeah, I mean, I guess many of these acronyms would not make sense, but I think DNF, CNF, OBDDs, BDDs might be things which are like commonly known. So as it is known, sampling from CNFs or finding point probabilities is NP hard. So which means that anything above a CNF is also going to be hard. So we're trying to characterize everything in this hierarchy. We know that finding approximate point probability in a DNF is easy, which means everything below a DNF is going to be easy. So we use these implications to find out about all of these classes, and only one class remains, the DNNF class, which is quite interesting, and it's been considered in many different areas like databases or just ML, for whether you can sample tractably from a DNNF. So that's the only open question. But for everything else, we settle the complexity of finding the distance. So going forward, these are the open questions which I'm looking at. How do we close this gap? We know that if the distributions were product distributions, then the complexity is big O of n. So if you have a high dimensional distribution and there's no correlation between the dimensions, it's just a product of individual Bernoullis, let's say, then the complexity is O of n. And maybe that could give us a hint, or maybe we could consider a mixture of product distributions or something to improve the upper bound. And we are also using this estimator to verify properties of language models. So as I said, the subcube conditioning kind of is similar to autoregressive models, where you can fix the prefix and condition on that, you generate the postfix. You can try answering questions like how far is a quantized model from the original. So let's say you have a model and you want to quantize it to make it faster, which means you want to remove a lot of bits from the parameters and have smaller parameters so that they run faster, or the size of the model is smaller. But you want some sort of a guarantee that once you quantize it, the distribution expressed by the model is not very far from the one you started with. Or maybe you're interested in finding out just how far it is. So these kind of questions now you can answer. Although it's nowhere, like nowhere close, because the n is very large, and also the distribution is on the discrete domain, like maybe on a dictionary of 50,000 tokens or something like that, not Bernoullis, which I have considered. So yeah, it's still polynomial, but it's a very large polynomial even now. So we're trying to improve it for this specific case. And you could also try answering questions like what percentage of students have submitted, let's say, LLM generated code on some assignment. So where you could consider that, you have a very large number of samples and some of them have come from a known distribution. So you could use this conditional access to improve the sample complexity of tests, whereby you can use fewer samples to decide whether there has been some plagiarism or not. So yeah, this brings me to the conclusion of the talk. So in this talk, we considered the problem of like distance estimation. And we considered gray box access and white box access. And we did not consider black box access because it's statistically intractable. But in these two models, we made some progress. For example, we created the first poly query distance estimator, and we also classified white box models according to the complexity of estimating distance in them. And we also implemented and tested our algorithms out for both white box and gray box models. So you can check out our tools at this link. So we have a tool called Berberic, where and there you can find the code and also our papers. So we'll work on making our algorithms useful for larger and larger models by finding more efficient algorithms. So that's the plan. Yep. Thank you.
Can you clarify once more, the lower and the upper bound are in exactly the same model in terms of allowed operation?
Yes.
Yeah.
The subcube condition.
And that's all.
And which one is correct?
I suspect the lower bound is correct.
That it's actually.
Yeah. I mean, it's rare to see n square as the real bound, right? So, yeah, I think the n might be the right one.
N or even slightly less than N.
So even for the very simple case of product distributions, the best on algorithm is still n, I think. So, yeah, if for product distributions you can't do better than n, I don't think.
I was just curious, what is the benefits for the lower bound on that?
I don't think they showed any. It might be something like n by log n plus 1 by or something. But yeah.
Do you know how much power, let's say, in terms of few conditioning you can, not the, you, because your model is restricting with the first few bits, right? If you
Yeah.
restrict any with the prediction that you take.
Yeah, that has been studied actually, but for uniformity testing, and they required root n samples, and that's tight. So it is a more powerful model, but it's, for example, we couldn't get it to work on the things we studied, and also we couldn't show a separation. Like, although it feels like it should be more powerful, but yeah, I don't have any intuition why it might be
The separation is beyond code and
not. So yeah, in this, the query was the prefix only, but you can also have an alternate model where you can fix any of the bits. And is that more powerful? So that's also a very interesting question. Even in that model, the n by log n is still the lower bound.